Hi and welcome to this tutorial on percentage yield. In the previous tutorial, we learnt about stoichiometry and how to calculate the masses and volumes of products and reagents using balanced equations. So in this tutorial, we're going to have a look, of course, at percentage yields and calculations involving percentage yields. So types of yields that you need to be aware of, we've got the theoretical yield and the actual yield. And the difference between those two values is what gives us the percentage yield. So what is the theoretical yield? It's the quantity of the product that should be obtained if the reaction goes to completion. So if it was 100%, for example. There is an assumption there that there's no transfer of chemicals to or from the reaction. So if you are transferring your mixture from a conical flask to a beaker, for example, we're assuming that every single particle in that conical flask gets transferred over. So there are a few assumptions within it. Now, the actual yield is the reality. So it's the actual amount of product that is obtained from the reaction when you've actually run it. And the actual yield is always going to be smaller than the theoretical yield. And you'll find there'll be quite big discrepancies if you're using school laboratory equipment, because it's often less accurate than if we're using really high-tech, expensive equipment in a professional lab. So a real life example would be Tom has 200 millilitres of milk and 50 millilitres of espresso coffee, and he combines them and blends the mixture before pouring the drink into a glass. So the theoretical yield is 250 millilitres, of course, because Tom had 200 millilitres of milk and 50 millilitres of espresso coffee. Matter can't be created or destroyed, so we're going to have 250 millilitres of liquid, theoretically, in the cup afterwards. But after Tom blended it in that blender and transferred it over to the cup, of course, some of the coffee remained in the blender. Not all of it was able to transfer over because they were in a rush, for example. So this is the theoretical, but the actual yield was 225 millilitres. That's actually how much of that coffee ended up in the cup in front of Tom. So that's a good example. We often have parts of the mixture left over in containers, etc. So let's look, why is the percentage yield not going to be 100%? Well, some of the product gets lost, of course. Some reactants don't react for various reasons, and we might make other waste products as well as the thing we're actually expecting, depending on the conditions. So I gave you an example of this first one, products being lost, transferring between containers. You try and minimize that because obviously you are going to lose some. And that example before with the coffee was a really good example of that. And especially with filter paper, for example, as well, you're going to lose some of your product incorporated into the actual filter paper. It's not all going to come through. And some reactants don't react. They might remain unreacted until the reaction finishes, and the waste products, side reactions might be happening at the same time with some of them, and some of the gas products might be lost as well. They might disappear into the atmosphere if it's not a closed system. So the percentage yield is just the relationship between the theoretical yield and the actual yield. So it's like a test. If the test is out of 50 marks, and you get 37 out of 50, your percent is 74%, of course, in that particular case. That's your percentage yield, because you had a theoretical 50, and then you had your actual, you actually got 37 out of 50, and you calculate the percentage. It's really, really similar, okay? So in the same way, you do actual divided by theoretical, if I can spell that properly, theoretical times 100, in the same way that you'd work out a test result percentage. So if I got 37 out of 50, I would do 37 divided by 50 times 100, and that would give me my score, my percentage for my exam result. And your units, of course, can be in kilograms, moles, and grams. Those are usually what you're going to be working in. So let's have an example. Let's have a go. We've got Tom back again. They're doing an experiment, and see if you can work out the answer to this. And of course, I'll go through a worked example too. Now, as always, my first step, if it's not given to me, is to write out the balanced equation. So I've got CH3OH. So I've got an alcohol and my carboxylic acid, COOH, and I'm going to make an ester in this particular case. Okay, so methanol and ethanoic acid, and we're making methyl ethanoate. So I've just written that out. I'm checking it's balanced. It is. Often with these larger formula, it's much, much quicker to see. Because of course, if I put a 2 in front of one of them, it's going to make a massive difference. Then I'm going to write out the relative molecular masses of the compounds. So my methanol, my CH3OH, is 12 plus 4, because I've got 4 hydrogens. I'm just going to group those all together, plus 16 from the oxygen, so 32. Then I've got my MR of my ethanoic acid. I'm going to put EF because otherwise I'm going to spend ages writing that out. 12 times 2, so I've got 2 carbons, plus 4, because I've got 4 hydrogens, plus 16 times 2, because I've got 2 oxygens, and that is 60. And then my MR of my methyl ethanoate is going to be 12 times 3, so I've got 3 carbons, plus 6 hydrogens, plus 2 oxygens, and that is 74. So I know that moles equals mass divided by MR. So I'm going to work out the moles. So N brackets CH3OH. That's me telling the examiner I'm working out the moles of methanol. So it tells me that 5 grams react. So I'm going to do 5 grams divided by my MR, which is 32. And that gives me 0.15625 moles. Then I'm going to look at the stoichiometric ratio. So you're going to have to jump back and look at your equation. They're all 1-to-1 ratios. So the moles of methanol and the moles of methyl methanoate are 1-to-1. Okay, they're both 1-to-1. So therefore, the moles of my methyl methanoate, I'm going to make the same amount of moles of it. So it's also going to be 0.15625. Fantastic. Now again, I know moles equals mass divided by MR. Therefore, mass equals moles times MR. So let's work out the theoretical yield of my methyl methanoate. So CH3OOCCH3. That is going to be my moles, 0.15625, my theoretical moles, times my MR of it. And I calculated that earlier, it was 74. So therefore I'm expecting, theoretically, 11.6 grams if everything reacts. Finally, I'm going to work out my percentage yield. So my percentage yield is going to be actual divided by theoretical times 100. So my percentage yield is going to be my actual yield, and it's 9.6, it's given to me in the question, divided by my theoretical, what I would expect if it fully reacted, that I've just worked out, times 100. And that gives me an answer of 82.8%. There we go. The previous question was quite long, wasn't it? It required quite a lot of working out. So do a sense check, okay? A yield above 95% or below 30% is pretty unlikely. And of course, you'll know which way around to put your numbers, because if you come out with a percent answer of 120, flip your numbers round. Okay, it's actual over theoretical. Of course, your number has to be below 100%.